So with that, I would like to turn it over to Dulep, and we will start our presentation. Thank you so much.
Okay, thank you, Jenny, and good afternoon, good morning, everyone, depending on what time zones you're joining in. I know we have a global audience, and sorry for that little glitch. Technology works when it works well, it works well. When it doesn't, we have that, but we were able to get this up and running, so that's great. I'm glad you could join us, and I'm going to talk about making statements of conformity. And basically, what it is, before in a calibration report, you calibrate something and you you call the the data point or the item you calibrate as a pass or a fail, and that's the basic of the things in there. But it's no longer a pass or fail or a binary issue. There's a lot more that goes in making a measurement, verifying that measurement, and call it within specifications. So we're going to talk about that and what has evolved in the measurement science, which is the metrology, the science of measurement. There is an accreditation standard for calibration and testing laboratories, which is the ISO IEC 17025. And the standard is what the calibration and testing laboratories get accredited to, and it is to determine their competence on how well they can calibrate and measure and provide test results in there. So before, traditionally, you send an item out to be calibrated, and a laboratory calibrates it and say, yes, the item is good. That means it passed, or it failed, and it failed a certain specification. So, and you took their word for them. But it is no longer the same kind of thing, because you could have the same item that is used by more than one different end user, and their requirements may be different than what you would call a pass or fail. So those are the kind of things as modern science and technology evolves, that makes it more complicated, and that is what we're going to talk about here. All right, so our learning objectives. Uh, that conformity decision is going to be based on a decision rule we apply for the conformance. And then that conformance requirement has to come from the customer. So as I said, the laboratory, the supplier that was the expert is still an expert, but they have to know your specific requirements. And then there is this uh, thing called measurement uncertainty, and the measurement uncertainty impacts a decision rule. And measurement uncertainty talks about all the errors associated with a measurement, because no measurement is perfect. And the measurement you make depends on a lot of other things, and the measurement uncertainty talks about that. And then again, our main item is, what do we call that item conforms to a requirement? And that's what we're going to talk about. And then anytime you make that decision, pass or fail, um, there is a certain risk associated with, and what is our appetite level for that risk, depending on the application where we're going to use that item for further, uh, decision making. We may use that item to make food products, pharmaceutical products. We may be making sure the speed of the aircraft is right, the amount of fuel that is filled in an aircraft is correct, and a lot of other applications and different risks associated with that. So This is just the typical thing we see. We calibrate a nominal value. That that value has a certain specification associated with that. And if that measured value, which is here in this column, 11.2, we know it is within the plus or minus uh, within 8 and 12, and we call it a pass. And that's what our traditional approach was. Yeah, it is within the upper and lower specification. So 11.2, we call it a pass. But is it really a pass? Now, this thing, measurement uncertainty, we said that calibration has a measurement uncertainty of 1.2 associated with that. Now, with that measurement uncertainty, is that a pass or fail? And that is what we're going to talk about in there. Now, within that standard that I talked about, there are three major requirements in that standard. So if a laboratory is accredited to the standard, they have to meet these requirements beside many other ones. But these are the ones I call the three pillars for making a good measurement. And the first one is, again, I alluded to this terminology, measurement uncertainty. And so laboratory is supposed to evaluate measurement uncertainty. And for the item that they're supposed to calibrate, they're going to provide you the associated measurement uncertainty with that measurement. So that is the first item. And if you look at graphically, we have certain nominal value. And in my example, I had that 10. And then we actually measured that. And then there is a requirement or a certain specification or tolerance associated with that. And that bell-shaped distribution is the measurement uncertainty associated with that. So basically what we're saying is that even though the measured value is what we measured, it could really be in that 95% confident interval. It would be the measured value plus the uncertainty reported at 95% confidence interval. So that value could fall anywhere in that measurement uncertainty the next time you measure it and so on. So graphically it is that. And the requirement for evaluating measurement uncertainty is in this ISO guide 98-3, guide to expression of uncertainty in measurement. And we call that GUM as an acronym. So when I talk about GUM, that is the document. And it is an ISO document. There is a exactly identical document, which is the JCGM 100, which you can obtain free if you wanted to know more about measurement uncertainty from this BIPM website. And the second part is this metrological traceability. Now, in the US, you hear the term, is it NIST traceable? And then it was measurement traceability. Now that terminology is redefined as metrological traceability, and there's a definition associated with that in the standard as well. And in this next slide, I have the definition in there. And there's some keywords in this: documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. And then if you look at this note, it says metrological traceability requires an established calibration hierarchy. So this unbroken chain of calibrations refers to this established calibration hierarchy in there. So remember I said common terminology, is it NIST traceable? No, nothing is traceable. And sometimes in the past, people have associated NIST report numbers with proof of measurement traceability. But those are the myths. What provides metrological traceability is the traceability through SI units, through our National Metrology Institute, NMI, NIST in the US, in Canada, NRC, and so on, CNAM in Mexico, just talking about our North American neighbors, and recognized under CIPM, Mutual Recognition Arrangement. So that's what established NIST traceability, no, metrological traceability, not NIST traceability in there. And how that happens is at the top of this pyramid, we have the BIPM, and BIPM is the International Bureau of Weights and Measures. That has one of the SI units, and I'll talk about the kilogram because they define the kilogram, and if that has an uncertainty of 0.005, NIST has its own kilogram, that has an uncertainty of 0.011. The 0.011 includes the 0.005, and so on. So documented, unbroken chain of calibrations, each contributing to measurement uncertainty. So measurement uncertainty is cumulative, and if somebody does not provide you the measurement uncertainty, then you don't have metrological traceability. So that definition is very important in that context, and that is our second pillar of measurement in there. And then our third pillar is about this topic that we're talking about. We take that information and we decide, is the item suitable for us, instead of the pass or fail. And so this part in the standard talks about saying, when you make a statement of conformity, you will employ a decision rule and take into account the level of risk, and then decide on the conformity or non-conformity of that item that is calibrated. Okay, so those are the three important things. And there are guidelines for decision rules. There's some very good documentation, and this International Laboratory Accreditation Corporation has this guideline on decision rules and statements of conformity. This is this ILAC G8, and you can download this document free of charge, and it's a very good, well-written document. It's written in English, it's not written in statistics, easy to understand, and I've got some information in here too, in my presentation, but if you want to discover this further, it's there for you. Okay, so there are some decision rules that are in there, but you could have a million decision rules if you wanted, in the sense that if you have a million customers, they could have each one of their own requirements. So within this ILAC document, they have these different rules, and as an example, and we're going to look at this ILAC G8 rule to illustrate our example in this presentation. And it says if we use this ILAC G8 2009 rule, it has a probability of false accept of less than 2.5% in there. So so we're going to use that in our example to say how do we interpret this statement of conformity, taking into account all these things in there. And what that decision rule does is it says, I have a nominal value, I have an upper and lower specification, I have a measurement. Right now, the way I show the measurement is, it is a perfect measurement. It means it is at the nominal value. I have a certain measurement uncertainty associated with that. And then depending on my decision rule, I subtract the measurement uncertainty or part of that measurement uncertainty, depending on the decision rule. And now I have an acceptance limit. So if my measurement falls within the acceptance limit, then I can live with that measurement with the associated risk associated with that. And then this region is called the guard band region in there. And I've shown you the example. So obviously the green measurement here is within my acceptance limit, which is fine. This second one here is right at the acceptance limit. So if I go any further than that, then it is not in conformance and I can't accept that measurement. And you could see, since we're testing this decision rule at 95% confidence interval, there is that roughly that 2.5% probability of false accept that we're willing to live with that if we use this decision rule. Now, a lot of times, a lot of people use this rule, but then I fly a lot, I travel a lot, and I said, do I want to get on an aircraft with a 2.5% probability of false accept? Obviously not. So for that, there are other decision rules in there. So I just wanted to emphasize that. So those three pillars of measurement, the measurement uncertainty, metrological traceability, and the decision rules. When we use them properly, and then we accept or reject that measurement, that provides us the confidence we need for our application. So this is how I call my measurement confidence. Without the three, I can't have the measurement and confidence that I need for my application in there. All right, so let's look at some things. Now, this is a very common statistics thing you may have seen. Sometimes it's called type 1, type 2 error. And now I'll kind of put it in the context of calibration. So if I calibrate something and I call it intolerance, and if I made a good call, then it is a good thing. But I called it intolerance, but if indeed it was out of tolerance, then this is this type 2 or beta error, or the consumer's risk. And then if I call something out of tolerance when I calibrate it, and I made the wrong call, it was in calibration, then I'm trying to figure out what's wrong, and there's nothing wrong. And that is the producer's risk, or alpha, or type 1 error. And so putting it in context of calibration or measurement in there. So ideally, I don't want to have that type 1 or type 2 error when I make a call based on the information I have. I want to make, if I call something good, I want to make sure it's good. And if I call something bad, I want to make sure it is bad. And then I can take the appropriate action on rejecting and making any corrective action in there. All right, so I like pictures, and pictures explain a lot of things in there. So here, I can make that same measurement with two different processes, A and B, or I can make that measurement with two different instruments. And then the associated bars associated with those A and B instruments or processes is the associated uncertainty. Obviously, if I use it with instrument A or process A, you can see the uncertainty is within my upper and lower specification limits, and there is no risk associated with that. And if I make it with the process B or instrument B, you can see there is this risk I'm taking, and that is my probability of false accept in that I have to take. Now, a lot of times I use this and say, I could have the same instrument, but depending on the application I use, I can choose to take the higher risk. And I use a lot of times an example of a tire pressure gauge. In the tire pressure gauge, you use the monitor and measure the pressure of a tire. And if I measured the pressure of my bicycle's tires, I could probably afford to take a higher risk. But if I measure the pressure of the tire of a commercial airliner carrying 200 plus passengers, then I probably need to minimize that risk. And so I better have a good gauge or a gauge calibrated, which would be that, because I can't afford to take that risk in there. So depending on the application, you could have the same gauge, but different risk associated with the application. All right, so let's look at our picture and simple acceptance. Simple acceptance is what we have used traditionally in making decisions. And basically we're saying, yes, is the measurement within these specifications? So I have a nominal value 10 plus or minus 2 here, 8 and 12. Yes, it is in. And the measured value is exactly 10, right at the nominal value. The measurement uncertainty is this 0.25. And I always like to look at pictures and I say, well, that is a good measurement. Simple acceptance, meaning not taking the measurement uncertainty into account. Now, that same measurement, it shifted. Now it is 11. Well, it is still within the specification limits, and there's no issues associated with that. Yeah, there's a slight tail end area out here, 0.003% risk, and yeah, I could probably live with that. And that looks very good. Now, I made the same measurement, but my measurement uncertainty is increased. So at that 11, measured value 11, my measurement uncertainty, now I have that risk I'm taking of the probability of false accept of 2.275%. So that is that A or B processes, and so those are the kind of things that we have to deal with in here. Okay, so now we're going to use this ILAC G8 2009 version decision rule, and basically it says you will take out 1/2 of the 95% confidence, the measurement uncertainty at 95% confidence interval from both sides of the tolerance limits, and then your acceptance limits become these two acceptance limits. And now we have that same measurement with a measurement uncertainty of 0.25, and we could say, okay, with that, the acceptance limit now is being calculated here, and it's not 8 and 12 taking the uncertainty into account. It's 8.49 to 11.51, and if my measurement is within those bounds, which 11 is, then it conforms, it passes, and I can accept that using this decision rule in there. Now, same measurement at 11, except I use a different calibration supplier. The uncertainty is double than what I had. And now my acceptance limits, are different because it takes the subtracts the uncertainty. And I am just barely at the limit, but if I'm anywhere beyond 11.02, then that decision rule will make me reject and not accept that measurement and that calibration. And I have to say it is does not conform, or it fails if we use the traditional word of pass or fail in that respect. Okay, so this is how the decision rules help us make the conformance decision in there. And here in this scenario, I've actually said, okay, now my measurement is 11.05, just beyond 11.02. And now it shows up as red in this little spreadsheet tool I have. And it says, yeah, I have to reject that measurement because the most I could take was at 11.02. And if the measurement goes beyond 11.02, I can't accept it. And you could see the risk, that tail end area is rising here with that measurement being beyond the acceptance limit in there. So going back to our original scenario, we have the nominal value, measured value 11.2, measurement uncertainty 1.2. If we used our simple acceptance, not taking the measurement uncertainty into account, we would have called that a pass. But now I'm going to employ this same scenario, and you can see the acceptance limit with that measurement uncertainty has significantly narrowed, and with the 11.2 measurement, it is a fail when I've employed a decision rule. Not employing a decision rule, meaning the simple traditional approach is that within the specification, does not do us any good here. And you could see we are taking a great deal of risk, the 9% risk in this case, that is going to be outside the actual specification of the instrument in there. So, the conformance decisions will be made on the decision rule, and the decision rule will take into account the measurement uncertainty of the measurement process in there. Now, all these definitions, the guard band, the acceptance limits, and those definitions are in that ILAC G8 document that I was talking about. Now, the current version is 2019 version. The previous version had this decision rule. This decision rule is very popular, so they've actually used that in the most current document in there. But just be aware that that decision rule is very conservative in nature. So sometimes it's good. Sometimes when things are conservative in nature, but sometimes you don't want to have too many false rejects as well. But it would depend on the application, where you're using the measurement result or the equipment associated with that measurement result. So, so what should you have in an ideal calibration report that an accredited laboratory provides? ISO 17025 accredited laboratory. So obviously the nominal value is what they're going to measure. The specification, the actual measured value, associated measurement uncertainty. So these are the most important thing, and by requirement, a laboratory that's accredited to ISO IEC 17025 is supposed to provide you measurement result and the associated uncertainty. Now, the decision rule, the acceptance limit, uh, will depend on the decision rule that you utilized. And in my example, I use that ILAC G8 2009 decision rule. So that you can determine using the tools you would have. But as a minimum, a laboratory should give you this. But when they give you this, they can't tell you it is a pass or a fail because they don't know your application. They don't know your decision rule. Now, if they want to, if you want them to provide that, then you got to give them more information. What decision rule? What is your criteria for acceptance limit? And that you as a consumer have to provide. Or you shop for a calibration provider that has much lower measurement uncertainty, and then you should be able to accept results on the measurement based on that information in there. So these things are important, that they provide you with the measurement uncertainty, and then the measurement uncertainty is also proof of metrological traceability that we talked about, and then we can base the decision rule associated using the measurement uncertainty of our provider. Now I have one column here, the test uncertainty ratio, and the acronym TUR. And you may see this in a lot of calibration reports. The test uncertainty ratio has been around, and a lot of people use that as a criteria for acceptance. And the criteria was if the test uncertainty ratio is greater than 4:1 or higher, then the calibration is good. But it is not to be thought about in that way because the test uncertainty ratio does not take into account the location of the measurement. It assumes when you make that 4:1 criteria that your measurement has no bias. And in this case, we had a bias between the measured value and a nominal value of 1.2. So it is misleading in that way. And we have better statistical tools available to determine our acceptance limit and calculate the measurement uncertainty properly in that way. So just kind of, these are the things I've reproduced from that ILAC G8 document. So you could see in the scenario, the traditional scenario, you have 4 scenarios with the traditional approach. You just have a measurement, and the measurement is within the specification limit, so it passes. Now we have a scenario, the measurement with the associated uncertainty, and in the first and second scenario, it passes because the actual measurements within the specification. And the third and fourth scenario, it fails because it's beyond the upper and lower specification. Now, we're still doing the binary pass or fail, and we're saying, okay, this passes, second one passes, taking the uncertainty into account, but we are using the acceptance limit. In the third scenario, the measurements with beyond the acceptance limit, but within the specification limit, so it fails. And then the fourth one, the measurements beyond the specification limits and it fails. So again, a pass fail, but now it's taking into account the acceptance limit. And the acceptance limit is this dotted line. You may not see it very well, and I reproduced these images from that ILAC G8 document, but you're welcome to download it. Now, if we take that non-binary, same scenario, you have a pass in that first scenario. The second scenario, the measurements within the specification limit, but beyond the acceptance limit. So it is a conditional pass. That means there is some associated risk you're going to take if you accept that measurement, and that's why it's a conditional pass. And the third scenario, the measurements beyond the upper and lower specification limits, but part of that measurement uncertainty is within the specification limit. So it is a conditional fail. And then obviously the fourth scenario, the measurement and the associated uncertainty is beyond the specification limit. So it is a fail for that scenario. But with these tools, with the decision rules, now we can make better decision and then decide on the acceptability of the measurement result based on the risk we're willing to take with that decision and the measurement result that's in there. So we use that G8, which is basically subtracting 1/2 of the 95% confidence interval. So that gives us a specific probability of false accept of less than 2.5% in there. And then they've given you the 6 sigma, 3 sigma limits, and the simple acceptance is the one which used to be our traditional approach. They mention that in here. I don't like it because it's 50-50 in there because your measurement is not taking the measurement uncertainty into account, and it's a lot of times called a shared risk. You could have your measurement within the specification at either end of the specification. So you have a 50-50 chance. So you're sharing that risk within the supplier and consumer in there. But these are the examples that are cited in that ILAC G8 document for making conformity decisions in there. And I mentioned that test uncertainty ratio. I've given you the definition here, and I say that is not a good decision rule that you should not use because it assumes your measurement is at a nominal value. So that's one bad thing about it. And we have better tools available to us now just in Excel. The previous slides I showed you with my was created using Excel, and that's how I was calculating those probability of false accept in there. So what should you as a consumer of calibration service specify? You should specify the exact data points you want in the range that your instrument measures. So if your instrument measures here, I've just given you an example, 0 to 100 grams, then you should say, okay, I want 25%, 50%, 75, 100% in there. And then for each one of those data points, you want the measurement uncertainty. And that measurement uncertainty should be calculated. Another ILAC document for ILAC P14 requirements. It says what you should have. A lot of accredited labs do not calculate the measurement uncertainty properly. That doesn't do us any good if they don't give you the right information, because we're going to use that to decide our acceptance limits and if they give us the wrong measurement. And that's why the three pillars of measurement, right? The measurement uncertainty that associates the metrological traceability. And then from that, we base our acceptance limits depending on the measurement decision rules we employ. So important to make sure that we do that. And then we choose the decision rule appropriate to the level of risk that we're willing to take. And I give you the example of a tire gauge, tire pressure gauge. For my, if I check the pressure of my bicycle with that, I could probably take a lot more risk. But if I take the pressure of the tire of the commercial aircraft, or a fighter jet landing on an aircraft carrier, which has a very short runway, then I want to take much less risk and make sure that gauge is calibrated, with a better standard, with a lot less uncertainty in that respect. So those are the kind of things you should watch out for from the consumer of calibration services. Uh, so you want a measurement result and the associated uncertainty. If you want your calibration provider to make the statements of conformity, then you should tell them what decision rule you want them to employ. A lot of the calibration providers will say, oh, we will use the simple acceptance. Simple acceptance is basically, is the measurement within the specification? It is not taking into account the uncertainty of measurement. I do not like the simple acceptance rule because that's the traditional approach. And the best thing you could do is you be the educated consumer, know about the decision rules, know about the measurement uncertainty, and choose a suitable calibration provider that can give you the appropriate measurement uncertainty, so you could make the decisions yourself, the decision of being in conformance or not being in conformance in there. Okay, so uh, just to wrap this up, we need to make sure we specify exact calibration requirements, including decision rules. If you're a calibration provider, then you want to make sure you understand the customer requirements. And then if you are making the decision rules with using the conformity decisions of pass or fail, then you need to employ the appropriate decision rule. And then it's a less misinterpretation of customer requirement. And then we're making better risk decisions, risk mitigation important in that respect. So this is not a new thing, but it's been around for a while, but there's more emphasis put on the 17025 standard. The current standard came out in 2017. And the reason for that is technology is getting better and better. We have better and better instrumentation available to us, and the standards to calibrate those instruments are not keeping pace. And so at the end user level, we have better and better instruments. The standards are not keeping pace with us. Um, so we have to, do this risk mitigation, look at the measurement uncertainty, and then everything we do has a risk associated with it. And in the measurement business, that is more and more important in that. So this issue of measurement uncertainty, metrological traceability, and then having the decision you make in there gives us better confidence in the measurement result that we obtain. And then we're going to use that instrument to make products, services that impact daily lives, safety, health, and a lot of those things that affects us. So I've given you sort of an overview of the things. Those documents that I referenced, those are available from the website. I will have the PDF of this presentation. I will have this available. I'll send it to Jennifer, and she'll be able to forward it to all of you. And now I will entertain any questions that you may have.
Yeah, there's been a couple of questions.
Okay, and if you read it, for some reason, my chat window is getting crunched, like it's overlapping. And the first one I'm looking, how do you adjust your acceptance limits for decision rule when the uncertainty distribution is not normalized, such as, and I'm trying to scroll down, it doesn't let me do that. So let's see. Such as, yeah, for some reason it doesn't let me scroll. So can you read that for me, Jenny, if possible? This is from Melissa.
How do you adjust your acceptance limits for the decision rule when the uncertainty distribution is not normalized, such as the one-tailed, rectangular,
Okay.
etc.?
Yeah. So, you could still do the same thing. There's a lot of things where, yeah, the uncertainty distributions part of the GUM that is normalized. Okay. So uncertainty is always reported as a normalized distribution. The uncertainty contributors itself may not be normalized, but before you combine them, you normalize them, and that GUM, the document I referenced, has guidance on how to do that. But a lot of times you have acceptance limits which are one-sided, and they're called unilateral tolerances versus bilateral, meaning the example I used here was 10 plus or minus 2. Sometimes you have 10, 0, n plus 2, or 10 minus 0 or plus 0 minus 2. So and you could use the same kind of decision rules here using the same kind of tools. Okay, but the uncertainty distributions always normalize. The GUM gives you more description on this in there. So that was a great question. Yeah, thank you. Any other question?
Yes, one of the other questions was, does the uncertainty variability include only precision, or is like the entire gauge R&R included?
Oh, this is a great question. So when people talk about gauge R&R, they talk about the automotive AIAG gauge R&R. Please do not equate gauge R&R with measurement uncertainty. I actually did a presentation somewhere down the line which said, what comes first, gauge R&R or measurement uncertainty? A chicken and egg dilemma. So the chicken and egg dilemma is easy. You order the chicken and the egg from Amazon Prime, whatever comes first, it solves your dilemma. But the the measurement uncertainty and gauge R&R is different. To summarize, gauge R&R, the traditional automotive AIAG gauge R&R, cannot be done if you don't have the uncertainty analysis done properly. Okay, so that's one thing. Now, let's talk about measurement uncertainty. Measurement uncertainty in the GUM requirement, and in my slide I said you look at the ILAC P14 requirements for what a calibration supplier is going to give, but it has got the A2LA, one of the accrediting bodies, has a good guideline on it, and I call that the 5 R's and an E. They said these are the things, 5 R's and E, you should consider: repeatability, reproducibility, but not the way the gauge R&R is done. There's a different way to do repeatability, reproducibility. Reference standard uncertainty. The environment, that's the E, resolution, and then the reference standard stability. So those are the 5 R's and an E. And that's the guidance that you should have in the uncertainty consideration. But just remember, the gauge R&R is not the same as the repeatability, reproducibility that goes in the measurement uncertainty evaluation. So that's one thing you should always consider. If you use the data from that traditional automotive gauge R&R, your measurement uncertainty is going to be over-evaluated. And if you have an over-evaluated uncertainty, you're going to fail things that you should have passed. Okay, that's a great question. So this allows me to explain that to you. So a lot of people do this wrongly, and they should not be.
What about when you do your uncertainty measurement calculations at like a controlled temperature and humidity, and then your actual process measurements might happen at a different environment? Would you need to consider temperature corrections?
Yeah, so the this 5 R's and an E, which is the environment, your uncertainty evaluation should be done at the conditions you're going to use or employ the measurement, okay? So measurement uncertainty should be done not in the ideal conditions in that way. It should be done at the appropriate. And when you consider this environmental contribution in measurement uncertainty, that takes into account the environmental contribution.
And the last question was about calibration intervals. Is it technically acceptable to monitor equipment wear between calibration intervals and statistically calculate future calibration intervals based on that wear?
Yeah, so this is a great question because in the 17025 standard, they talk about doing intermediate checks in between calibration intervals. Okay, because and the worst thing you could do as an end user of an equipment is you have the calibration interval, and then you have something calibrated and it comes out of calibration. Now you have no idea at what point in time your equipment went out of tolerance. But if you were doing intermediate checks in between, you would have an idea to send it back for recalibration, repair, etc. So that's one thing in there. And then the calibration interval, the calibration provider should not impose a calibration interval. The consumer of the equipment should specify, because the supplier doesn't know how you use the instrument. You know how you use the instrument, and then you should monitor yourself the in between the calibration interval, those intermediate checks, to decide how appropriate it is. Now, there's a lot of advantages to this, because if your equipment is stable, you can obviously increase the calibration interval, or if the equipment is unstable, you can shorten the calibration interval. Now, there's a great, I mentioned that ILAC website in my presentation. There's a ILAC G24 document that addresses how you can kind of determine calibration intervals. It's again a very nice document, very simple. There are other guidance documents that are more complex, but this one is done very well and gives you some very good examples. Now, this document is under review, but the one that is current, that came out in 2007, is still excellent. And the reason it's review is the 17025 standard got revised, and they're going to, I think, revise the references to the new standard in there. But it is still a good document. So when you go to that ILAC website, look for the ILAC G24 document, and that talks a lot about the calibration interval. They've got like 5 approaches, and they do a nice job. Simple document. The other one is an NCSLI recommended practice one, but it is more complex. It is a good document if you have thousands of artifacts of calibration, and it does a very complex statistical approach of determining. For example, the US Navy does that, but US Navy has thousands of artifacts, and the one gentleman who's retired from Navy now, but that I know, he used to do that interval analysis, and he could tell you, if you say, I have this instrument model, what is the calibration interval for this? And he would tell you, yeah, it's 5 months, 2 days, and 3 hours. But they had the population to do the appropriate statistics. A lot of times, smaller organizations and even larger organizations don't have that large population of one make and model of that instrument to do that determination. Okay.
Okay, well, that was really great. I think that brings us to the end of the webinar. Really appreciate your presentation, Dilap. That was another great presentation as usual. And I appreciate everyone hanging in there with us for the presentation. I'm sorry for the struggles we had with the technology today. We will be posting the slides and the recording and all of that, but if you have any questions, feel free to email me. Thank you very much.
Thank you, and it was my pleasure doing the presentation.
All right, goodbye, everyone.